Hello everyone, this is my first attempt at recording this class offline and making it uploaded to and reaching out to you via YouTube. So please bear with me as I try my best. So let's get started. We will be completing the packet on chapter 8, laminar flow. It seems like last class we couldn't complete one problem, which is laminar flow in a pipe. This is I think towards the end of the packet, and this is an important problem. It pretty much goes through some of the concepts we learned already before the spring break. So let's get started on it. Okay, so laminar flow in a pipe. This problem says fully developed laminar flow of glycerine at 40 degrees Celsius passing through 100 meter long 0.1 meter diameter horizontal circular pipe angled at 10 degree upward. So for now, let's just cancel this. Let's look at if it is just normally. There is no angular bend, so it is 0 degree. The flow velocity at the center line is measured as 5 meter per second. So that is, center line means V max. So we are to find out what is the velocity profile, pressure differences along the length of the pipe, useful pipe, and useful pumping power required to maintain the flow. And these are the parameters which are being provided. Glycerine is at 40 degrees Celsius, density is so and so, and mu is 0.3. Okay, as I said, first let's look at 0 degree. There is no angular bend, and we have to really find out. The most important thing is the flow laminar. That is the most important thing to find out. And so for part A, what is the U of R? For the laminar expression, you have U max 1 minus small r divided by capital R, and this is a square, so that is distance from the center. So U of R is 5 meter per second, 1 minus r square, and capital R is a diameter. So diameter is 0.1, so this will be 0.05 square is equal to 1 minus 400 r square. Okay, so this is the expression for U of R. Now let's look at the pressure difference along the length of the pipe. So for this, go back to your notes from the past. We looked at, if you remember, this expression delta P as a function of average velocity, length, and the radius of the pipe. So we will use this, and so delta P, it will be 8 mu L V average divided by R square, which is 8 mu L. V average for laminar flow is V max divided by 2 R square, which is 8 times mu is 0.3073 times L is 100 meter long, and Vmax by 2 is, Vmax is 5 meter per second, so 2.5 divided by R is 0.05 square. So turns out when you do the calculation, 2.84 kilopascal. Okay, so now that we have this information, we have to check if flow is laminar. How do you do that? Reynolds number, always remember that. So it is, for this particular case, it is around 1000. That means it is laminar. And so we could have also used for delta P this expression, the Darcy's friction factor, right? 64 RE, L is 100, 0.1 rho V average square by 2, which is 246 kilopascal. So this is similar to what we found here. Okay, all right, so what is the last part? We have been asked useful pumping power required to maintain the flow. So pumping power is directly proportional to your pressure drop and also a volumetric flow rate. Right, so that is the pressure drop dictates how much pumping power you would need. So volumetric flow rate, which is like with a dot on top, V average times area, cross-sectional area, times delta PL, which is 2.5 meter per second pi 0.05 square times 246,000, that is 246 kilopascals, which is equal to 4.83 kilowatt. Okay, so this is in the case where you have no angular bend or elevation. So if we were to have this for the same pumping power, the question is, how does flow rate change if your angle is 10 degree upward? Okay, so how do you attempt such a situation? So your volumetric flow rate is given by your pump power divided by pressure difference, correct? From this equation. Okay, we know we are keeping the pumping power fixed, so it is known, but delta P will be different. So how will you find out delta P in this case? Always remember that whenever you are asked to find out pressure differences across a pipe, your best bet is, if it's something related to delta P is unknown, always use your energy balance equation from chapter 5. So in this case, P1, the entrance, rho G, plus alpha 1 V1 square over 2G, plus Z1 plus H pump U is equal to P2, the outlet, plus alpha 2, the correction factor, V2 square over 2G, plus height Z2, plus if you have a turbine, plus HL, head loss. Right now it's a laminar flow. V1 and V2 are equal, so this is equal to V2, this is equal to V1. So P1 minus P2 is equal to delta P is equal to Z2 minus Z1 plus HL rho G. What is Z2 minus Z1? Height difference. This is where your angular elevation or angular orientation of the pipe comes into play. So the height difference is always L times sine theta. In this case, L sine 10 degrees. Right? What about HL? We have calculated it above. It's equal to delta PL over rho G. It's equal to 20.03 meter. Right? So you plug it in. Your delta P is 1252 times 9.81. Right, so this is the rho and the G, times L is 100 sine 10 degrees plus head loss is 20.03, which is essentially 4.59 times 10 to the power 5 pascals, or 459 kilopascals. And your volumetric flow rate is 4.83 kilowatt divided by 459 kilopascals, which is equal to 0.105 meter cube per second. So this versus 0.0196 meter cube per second before, when there was no elevation. So you can see the difference here. It's certainly the flow rate is affected, and this is the difference. Okay, so that completes our laminar flow in pipes. Now you can go to your second packet, which was handed out to you in class. For those of you who are not present, these packets are also uploaded on your Canvas. Look for it. It's the second part of chapter 8, which deals with the turbulent flow in pipes. So turbulent flows is rather very complex, and we don't have closed form expressions. So that's what makes it really challenging. And one of the reasons why we do not have closed form expressions yet is because of the chaotic nature of the flow. Okay, so turbulent flow dominated by fluctuations, eddies, which is really the chaotic part of the flow, and it increases transfer of momentum, heat and mass, also increases friction, and this is essentially stochastic modeling where you have balls of same colors stacked up just to show pictorially what happens. This is before turbulence. After turbulence, you can see all the different colors are jumbled up. Velocity of as a function of time is really like the stock market happening now, fluctuating. Actually, this is a pretty good picture. It is like our heart rate probably fluctuating, but at the same time that's why you take the mean value and the standard deviation. So this is like a snapshot of a turbulent flow. You can see the chaos inside of it. It's pretty complex. And phenomenologically, eddies in flow increase the friction, increases shear stress at the wall. So that's why we have something known as a total shear stress. And conveniently what we can do is you can separate out the shear as laminar plus turbulent. So laminar would be straightforward, mu du over dy. This is Newtonian. Turbulent, you have mu t, which is the eddy viscosity, hence du bar over dy, which is essentially this, the mean you take. Okay, and y here is r minus r, which is distance from the wall, and here is the concept. So mu t, again eddy viscosity, counts for momentum transport via eddies. Eddy motion very high at core of flows and low or near zero near the wall, near or at the wall. Why? Because of the no slip condition, which must hold. Unmeasurable and does not depend on fluid properties but on flow conditions. Okay, so visually we can break down the flow profile into sublayers. There is a turbulent layer, where your eddy motion is very, very greater than viscous motion. Essentially, this is, the roots are in the molecular level, and this is a pretty much a flat, slowly changing profile. Next, you have what we call is an overlap layer or a transition layer, where the turbulent effects are significant, but not as dominant. And this is pretty much like it's a logarithmic profile. Then you have the buffer layer, which is this, where viscous effects dominate, but turbulent effects still present. And finally you have the viscous layer, which is very thin, quantitatively it is like 0.01 of the diameter, and it's a linear profile. And your thickness of this layer is 25 times your viscosity divided by the velocity at edge of the layer. This is a kinematic viscosity, by the way. And it gets thinner as the Reynolds number goes up, and thus your overall profile becomes flatter as your Reynolds number goes up. And this is very important because your thin wall layer controls the entire profile shape, and we will go over it if we have time later in this chapter, where we discuss Reynolds number and the thickness of this layer as a function of Reynolds number, how this layer becomes thin or thick depending on the velocity. Okay, so approximating the profile, as you can see that this is not an easy thing to really capture using an analytical form. That's why you have something which is approximate expression using a power law. U over U max, Y, and Y here is R minus R, which is your capital R minus your small r, which is distance from the wall. Right? And so this is one expression used where n is an integer, and this value of n increases as Reynolds number increases. Just to put into perspective, if you have u velocity, u max y over r 1 to the power n, you take the derivative u max 1 over n y 1 minus n power n times 1 by r raised to the power 1 by over n. This is y raised to the power 1 minus n divided by n. Okay, so 1 minus n, this exponent is always less than 0, right, for n if it is a greater integer than 1. So what happens at u dash at y equal to 0? It almost reaches infinity, approaches very high number. That is the real concept behind using this power law. However, what people have found is that n equal to 7 works well for many flows for industrial applications. And you can see here, this shows u over u max and r over r. N equal to 6. This is a laminar flow, the blue line, and this is how your n changes. What are some of the limitations of this equation? It does not have zero slope. You can see here how the slope is slowly progressing. It does not have a zero slope at the center of the pipe. And you cannot calculate stuff like shear at the wall, just tau W at the wall, because du over dy at y equal to 0, it approaches infinity. Okay, so going forward, we have seen here in this profile the most important thing for a turbulent flow here is the thickness of the thin layer here, the sublayer thickness. Essentially, this thin wall layer is pretty much controlling the entire profile of the shape. So we want to know, what if the thin wall layer had some irregularities or ridges, or it was not a smooth surface? What will it do to the entire shape profile? And this is a problem which plagued the community, the fluid mechanics community, back in the early 1900s, and that's where this whole field was erupting as a major research topic. That's what we will be seeing, how engineers actually came up with simple empirical tools to characterize this effect. So surface roughness is a very important term here versus turbulence. So surface roughness, as the term itself implies, has to do with the smoothness of the wall and how does it control the overall profile. So again, recalling, wall sublayer very thin controls the profile shape, because of the ridges disrupts that layer if the ridge size is similar, and we'll see that. Okay, but a perfect world is a surface is hydrodynamically smooth if wall sublayer submerges roughness elements. Examples: we have smooth layer surface, glass, most plastics. However, in reality, most pipes, even till date, we have most surfaces are rough at high magnification. That is why we consider something known as the relative roughness, or the ratio of E to the power capital D. Okay, so E here, it is essentially the ratio of mean height of roughness to pipe diameter. That is D. And this is the mean height of roughness, which is E, or epsilon, however you want to call it. So as usual with turbulent flow, effects of roughness not analytically tractable. Grad students did lots of painstaking experiments in the 1930s to get relationships. These included glued sand grains of specific sizes to pipes, etc. And so one of the first solutions which were proposed was what we call it as the Colebrook equation, which gave a analytical form to the friction factor versus roughness. And this particular equation, as you can see here, your friction factor F shows up on your left hand side as well as your right hand side. So what do you do when you have a variable showing up on both sides? For such an equation, what you do is you put in your guess on right hand side and solve put in result again on right hand side and keep doing it iteratively until there is a convergence. So this is an explicit equation for F, approximation of Colebrook. This is really handy right now, the way it is presented, the final form, because what you can do is now you can plug in your Reynolds number and your roughness, the mean height of roughness and the diameter, and pretty much predict the friction factor. And this is what the form which is right now used by engineers. These are mostly in handbooks which most chemical engineers carry around in the field. And note that whatever answer you get, depending on your relative roughness and the friction factor, it is not the exact, it is not the most accurate one. There is always a plus minus 2% error involved, or it could be more. Okay, and so this is one way to go about it. But here the problem is you still have to know the flow, the Reynolds number, right? And if you are in the site, you sometimes might be struggling to determine the Reynolds number, because who is going to find out what flow parameters are inside of the pipe? So what people did was they came up with something known as a Moody chart, which is still very, very effective. And this gives you friction factors as a function of Reynolds number. and it is based on the Colebrook equation. It's an extension essentially, and this is also there available in your appendix of your textbook. Look for it. But this is the chart, which is the simplified version shown here. What you need to really know, as a function of Reynolds number, how does your friction factor change? Okay, so the chart basically has a number of plots, number of lines, which will tell you if the flow is, which as a function of Reynolds number you should be able to predict the friction factor. So this, initially when you start out, there is a linear dependency with F and RE. This is the, what we call it as the laminar flow. Laminar flow, your friction factor goes down with respect to Reynolds number increasing, and it is independent of E over D. Okay, you go slightly above it, as you go on increasing in Reynolds number regime, you get into this fuzzy region, which we call it as the transitional region, where the flow is transitioning from laminar to turbulent, and the flow could be laminar or turbulent here, or it could even alternate. And depending on that, your friction factor alternates too. The other thing is, data here is not reliable. Okay, now you go beyond, you go on increasing the Reynolds number, and suddenly you see here that you are getting into the turbulent regime. The turbulent regime, one interesting line you see here is that your friction factor and Reynolds number, they are very much dependent on E over D, the ratio of mean height of roughness to the pipe diameter. Depending on this ratio, you are going to get these curves. However, there is a red perforated line. This line marks the point past which flow is fully turbulent. F becomes independent of Reynolds number, and your wall layer so thin, becomes so thin at this point that is negligibly small compared to E over D. And your Colebrook equation reduces to von Neumann equation, which is 1 over square root of F is equal to minus 2.0 log epsilon over d divided by 3.7. So these are analytical expressions. Oops. 3.7. Okay, so this is very important, and so these are the two tools basically you have: Moody chart and your Colebrook expression for relating friction factor and Reynolds number and roughness in a pipe in the thin layer which controls the shape in a turbulent flow. And finally, some final notes on friction factors. This is from a design perspective. What can affect a pipe's roughness? Material itself. It can scale. Material itself, it can build up over time. Corrosion is an effect. And you should remember that roughness when new is not the same as roughness after years of use, and this usually increases over time. When using Colebrook equation or Moody chart, note that they are not necessarily accurate. Errors can be as high as 15%. It's very important. And D, the D what you use in the E over D expression, epsilon naught over D expression, is it's the actual inner diameter of the pipe. Okay, so that is very important. Okay, now let's try to do a quick multiple choice problem using these empirical relationship what we just understood. Okay, so flow through a 2-inch diameter steel pipe reveals that the Reynolds number is approximately 5 times 10 to the power 5. If the velocity was increased by 10-fold, how much do you expect the friction factor to change? Okay, so this is, if you were asked this question, the choices you are presented with are decreases, remains constant, increases by 5%, increases by more than 5%. So these are the choices you are presented with. How would you go about? First, always look at the material of the pipe, steel pipe. So for steel pipe, what is the expected value for E? The diameter is given 2 inch, right? So let's look at the E value. Your E value, if you go to your slide here, steel pipe, commercial steel pipe, 0.00015. Okay, in millimeters it is 0.045 millimeters. Okay, so what is your E over D value? 0.00015 feet divided by 2 inch feet divided, you're changing the unit conversion, so it's around 9 to the power minus 9 to 10 to the power minus 4. Okay, so now you have this E over D value and you have to relate it to your friction factor F and Reynolds number, which is 5 into 10 to the power 5. So these 3 parameters, which chart gives you that? It is the Moody chart. Right, so let's go back to the Moody chart. So your Reynolds number here is 10 to the power 5, right? And your E over D value is 9 into 10 to the power minus 4. So somewhere around here, right? So 10 to the power 5, this line. So E over D value is say around 0.001, or yeah, around that. So now if you increase the question is asking, if you increase the velocity by 10-fold, that means you're going to increase your Reynolds number. You are probably going to see a decrease, a slight decrease in the friction factor. This decrease. And this decrease is not significant. So you can pretty much guess based on your options that decrease by 5%. This is how you can approximately guess how much decrease or increase you can expect depending on your E over D value, friction factor, Reynolds number. This is how you use the chart. So first calculate this value based on what is provided in your Colebrook equation chart. Then connect this, use this information along with F and RE in your Moody chart, and you can get a qualitative, semi-quantitative feel of whether there is a decrease or increase and by how much. Okay, so this is one example. Okay, now that we know how to use the Moody chart, why is this stuck? Okay, it was frozen for some reason. Let's look at the types of fluid flow problems, what you'll be dealing with and where you'll be applying this empirical relationships and your equations. So there are 3 types of problems you can anticipate here, and essentially the governing equation is what we saw, delta P or head loss is equal to F L over D rho V average square by 2 for a laminar flow. But since we could be dealing with either a laminar regime or a transition regime or a turbulent flow regime, the empirically used set of equations to find out if you are asked for the first type with the pressure drop or head loss, and you are given LD, length of the pipe, the diameter and the volumetric flow rate, or any of these combinations of these parameters here is essentially a set of three equations, what we call it as the Swamee-Jain, SWAMEE-Jain formulas. So these are empirical equations which are used as a semi-quantitative way to solve it. This is like really a handbook of equations for a chemical engineer, and it is usually accurate to within 2% of the Moody chart. The other thing is that you can use them also as initial guess if doing iterative calculations. Okay, so this is one way. The other way is typically you can pretty much start from this analytical form of expression and then calculate F, E over D and other things. You can lay it down using different Colebrook equation or the other empirical equations, and then solve them using a solver. So we will see that in this example. Okay, so this is a diameter. The problem states that you have to find a minimum diameter of a duct, air duct, and inside the duct you have heated air at around 1 atmosphere and 30 degrees Celsius to be transported in a 150 meter long circular plastic duct at a rate of 0.35 meter cube per second if the head loss in the pipe is not to exceed 20 meter. Determine the minimum diameter of the pipe. You have the density mu and this given V, right? So how do we go about solving D? So look at, this is the third type of problem, right? So here you can use this expression. So let's start with the assumptions. Assumptions is steady flow, incompressible, fully developed flow, no bends, valves, etc. It is ideal gas. Smooth, that is epsilon naught or E is equal to 0. Is it turbulent? To be found out. So possible solution strategies. Swamee-Jain formula, the third type, which is explicit. The other thing is, as I said, write down from this fundamental HL equation and calculate. You can iteratively solve this set of equations using a solver. So write all relevant equations and solve simultaneously. Oh, sorry. Okay. So explicit correlation, which is the third equation in the Swamee-Jain formula. D is 0.66, E 1.25, L V flow rate square divided by G HL raised to the power 4.75 gives me 9.4 L G HL times 5.2 0.04, which is equal to 0.66. E is here equal to 0, smooth surface as we said, plus 1.655 times 10 to the power minus 5 meters square per second, 0.35 meter cube per second, which is a volumetric flow rate, raised to the power 9.4. Length is 150 meter. G is 9.81 meter per second square, and head loss is this value, 20 meters. Everything raised to the power 5.2. And this whole expression exponent is 0.04. Okay, so you get a D value of 0.271 meter. Okay, so this is one way to do it. You feel free to do it, but I also want to show you simultaneous solution, which is essentially starting off with your foundational equation, which is the form which you saw. HL or delta P is equal to F, the friction factor, LD, L divided by D, V square divided by 2G. So you need to find diameter as a function of HL, etc. Right? So this is the form. So what is known? We know HL, length G, unknown, friction factor, diameter D, and V. So we need equation. This need to be found. This is the goal. We need equations for F and V, friction factor in V. So for F, what do we use? The Colebrook equation, very convenient. 1 over square root of F is equal to minus 2.0 log U over D 3.7 plus 2.51 Reynolds number this. Right, this goes to 0 is equal to 0, equal to minus 2.0 log of 2.51 Reynolds number square root of 5. So now we are stuck with unknown of RE, so we also need the knowledge of RE. Reynolds number. So for V, volumetric flow rate divided by cross-sectional area, 0.35 meter cube per second, pi d square over 4. From here also RE, Reynolds number, V times the kinematic viscosity, velocity times diameter divided by kinematic viscosity, which is 1.655 times 10 to the power minus 5 meter square per second. So these set of equations, now you solve this simultaneously. In MATLAB, or from alpha or any solver, and you can get D, but you find D is 0.267 meter. F is 0.0180, V is 6.24 meter per second, and your Reynolds number, when you solve it, is this value. Now, what is the advantage of this route? It is very similar to your previous solution. However, this is more accurate. I personally prefer this route because it is based on analytical expressions rather than relying on someone else's empirical formulation. But it's your choice. You can go this route, this tedious route, or you can simply plug and play using the Swamee-Jain formula. So that's pretty much it about turbulent flows and how to use charts and roughness, thin wall, friction factor is the most important concept here. Please go through this lecture again if you have some time, or go through your textbook. Next class we will see minor losses and how to approximate losses based on what category we are looking at, major versus minor. Okay, thank you.